So this is going to be my second video on work, and specifically in this video, I want to focus on spring problems, so problems involving springs in calculus. So the first thing I need to talk about is Hooke's law, which basically says that the force required to keep a spring in a compressed or stretched position x units from its equilibrium position is F equals K times X. Now I'm going to point out every spring kind of has its natural resting position. And so what this is saying is if I try to compress it or if I try to stretch it out X distance from this normal resting position, it's going to take a certain amount of effort. And so what that is again the force F equals K is going to be a constant. It's just going to be a number times X, that distance from its equilibrium position. Now, K is just representing how stiff or how rigid that spring is, how much effort it's going to take for me to move that spring any. So I'm going to go ahead and just jump into an example, and I'm going to talk about real quickly. Suppose a force of 10 newtons, so there's F, is required to stretch a spring 0.1 meters from its equilibrium position and hold it in that position. So before I jump into this problem and get too far involved in it, I want to remind you that newtons and meters kind of go together as far as units. So if it gave it to you in centimeters or millimeters, you're probably going to want to convert it to meters just for ease of use and making things work out nicely. Same thing with feet and pounds. If it gives it to you in inches, you're probably going to want to convert those inches to feet just for best results. Now, getting back into the problem, it says, assuming that the spring obeys Hooke's law, find the constant K. So essentially, I need my force equals K times X. The force in this case is 10 newtons. K is what we're solving for, and we know that it is 0.1 meters. So I'm just going to divide by 0.1 meters, which should give me 100 newtons per meter. And that is going to be my spring constant, K. From here, I want to talk about how much work is required or how much work is needed to compress the spring 0.5 meters from its equilibrium position. So we can imagine we have this spring and it's in its equilibrium position, and I want to compress it. I want to shrink it down by 0.5. Now, what that's meaning is that if this is 0, at its equilibrium position, it's actually ending up at negative 0.5 as its resting position. I need to know that because if you recall from the last video, the work is defined as the integral from a to b of f of x dx, where f represents our force over x, the distance. Well, our force, given by Hooke's law, is F equals K times X. Lucky for us, we just found K in part A. So, in this situation, our work is going to be the integral from 0 to negative 0.5. That's its ending place, its compressed position of 100 times x dx. And so I'm going to integrate that, and I want to remind you all that that's going to turn into 100 times x squared over 2, but x squared over 2 can be simplified with that 100 to make 50x squared. And we're going to integrate that or evaluate that from 0 to negative 0.5. If I plug in 0, I just get 0, so I really need to do 50 times negative 0.5 squared. Lucky for us, that squared is going to make it come out positive. That's going to be 1/4 times 50. So the final answer here will be 12.5 joules. Again, you could also write this as Newton meters or Newtons times meters, but joules is definitely the more accepted unit for work. Two more problems. How much work is needed to stretch the spring to 0.25 meters from its equilibrium position? So again, if I imagine this spring starting out in its equilibrium position at 0, I want to stretch it out 0.25 meters. So it's going to start at 0, end at 0.25. Still keep that force 100x dx. When I integrate, still going to get the same thing, 50x squared, evaluated this time from 0 to 0.25. So again, if I plug in 0, I just get 0. If I plug in the 0.25, let's see, that's going to be 1/4 squared, which is going to give me 1/16 times 50, which should be 3.125 joules as my final answer. And the last one is how much additional work is required to stretch the spring to 0.25 meters if it is already stretched to 0.1. So I'm pointing out that it's already stretched out a little bit at the 0.1, and what I want to do is I want to stretch it out to 0.25. And it's asking me how much work, how much new work is it going to require to stretch it that much further. So I'm going to put my lower bound at 0.1, my upper bound at 0.25, still have that 100x dx as the force part. And again, when you integrate it, you're still going to get 50x squared. And my lower bound is 0.1 and my upper bound is 0.25. This time I will have to actually plug both of those in. So let's see, 50 times 0.25 squared minus 50 times 0.1 squared. Let me grab my calculator quick. 50 times 0.25 squared minus 50 times 0.1 squared should give me 2.625 joules. All right. And that is the end of this. Hopefully this helps you guys make better sense of spring problems. I hope to see you guys in the next video.